This video is about independent and dependent events. Jumping right in regarding independent events, the occurrence of one event does not affect the probability of the other, and their probabilities multiply together. The formula, where the symbol for and is the upside down U with no tail on it, is equal to the probability of the first event times the probability of the second event. Looking at the example, we have a six-sided cube. Now this is not a standard one because the sides are numbered in the following fashion. And then they have sides that are colored. 4 sides are colored red, 1 side is white, and 1 side is yellow. Find each probability. So you have to be careful and read the problem to see if it's going to be a standard six-sided cube or not. Tossing a 2, then a 2. Now this word then is not meant to say like you get a 2 and then what's the probability of getting another 2. It's just like you toss a 2, you pick up the number cube and then roll again. So these are independent probabilities. So the probability of rolling a 2 and another 2, just multiply the separate probabilities together. Probability of rolling a 2 on this number cube is number favorable. There are 2 2's over total possible number of sides, 6. And the probability is the same when we want to roll another 2. Reduce, simplify before you multiply. A third and a third make a ninth. You could also write that as 11.1 repeating percent or as 0.1 repeating. The decimal percentage or reduced fraction represents probability. In the next example, tossing red, then white, then yellow. Again, it's independent because I'm going to toss a red, pick up that number cube, then toss a white, pick up the number cube, then toss a yellow. One is not affecting the other. So the probability of rolling a red and a white and a yellow is the product of their individual probabilities. Remember, this is not a standard colored die either, so their 4 sides are colored red. So 4 favorable over the 6-sided dice, 6 total. White, there's 1 of those sides, and yellow, there's 1 of those sides. Simplifying before I multiply. 2 into 4 twice and into 6 thrice, and then 2 into 6 thrice. So I have a ninth times a sixth is equal to 1/54. For independent probability, the separate probabilities are independent. One does not affect the other. For dependent events, the occurrence of one does affect the probability of the other. Then we have this notation where this vertical bar is for given. And this reads that the probability of A and B both occurring is equal to the probability of A times the probability of B given that A has already occurred. For our 2 examples below, we have 2 number cubes are rolled. It doesn't say anything about the sides, so we're to assume that they're standard. They're numbered 1 through 6. We're going to distinguish one cube from the other by their color. One is white and one is yellow. Explain why the events are dependent. Then find the indicated probability. I will explain without writing down why they are dependent. The white cube shows a 6 and the sum is greater than 9. The fact that I already know that the first number cube shows a 6, and my goal ultimately is to get a sum greater than 9, they are dependent because if I have a 6 on the white, then I could only roll a 4, a 5, or a 6 on the yellow to get the sum that's strictly greater than 9. So this will be the probability of showing a white with a 6 and the sum is greater than 9. So I get to multiply those two probabilities together. The white 6 is the first domino to fall, so it's independent, just its normal probability. But then the fact that the sum needs to be greater than 9, that is dependent. So probability that the sum is greater than 9 given that vertical bar that we already rolled a white 6. Now, the number cubes are being rolled at the same time, but just kind of think about it as one, and your eyes catch that the white one already shows a 6. Before you move your eyes to the second number cube, you could already start thinking about, if your goal is to get a sum greater than 9, you could understand what your chances are. The probability of rolling a white 6 on a standard number cube labeled 1 to 6 is 1 in 6. Now, like I showed before, given that we have on the white number cube a 6, we only have to get strictly greater than 9 for our sum 4, 5, and 6 as the favorable options on the faces of the yellow cube. So 3 favorable over 6 possible. Simplify before you multiply. Half times a sixth is a 12th. Those probabilities are dependent because the fact that we start off with a 6 restricts us to certain number of faces on the other number cube. Looking at the next example, the yellow cube this time shows an even number. Well, for even numbers, there are 2, 4, and 6. So right now we might think that we have a 3 in 6 chance of getting a yellow cube that shows an even number, but that's not taken into account the connectedness between these two probabilities, between these two number cubes. The other part of the problem is that we also and ultimately want the sum to be 5 between the two number cubes. Well, 6 is already greater than 5, so that invalidates that as an option. So really, we have a 2 in 6 chance of rolling a number cube that shows an even number and ultimately getting a sum between the two number cubes of 5. So we have a probability that we have an even number showing on the yellow, and we also want a sum of 5. So we multiply the two probabilities together. Even yellow will be by itself, its normal probability, and with respect of seeing down the line that we want the sum of 5. So it's probability of a sum of 5 given that we already rolled an even on the yellow, so to speak. So the probability of an even yellow, as I covered, we do not count 6, so we have 2 favorable over 6 possible. And I've shown that here. These are now our sample space. There are 12 of them. 12 possible options now for us to get a sum of 5 with the next roll, with the next number cube. The sum 5 only happens when the white number cube is going to be a 3, or the white number cube is a 1. So then that's 2 on 12, which reduces to 1/6. That's using the approach of like drawing out the sample space, that is your denominator, and then picking the number of favorable outcomes from it. There's another head-on way to get this answer. Think of the following. Once you know that a 2 is already rolled on the yellow number cube, you only have one option out of 6 to get a sum of 5 in the end. So the fate of the first number cube, so to speak, is already decided. Or, consider the following. The first number cube, yellow, shows a 4. Now there's only, again, one way to pair up with that to get a sum of 5. So again, 1 in 6. 1 in 6. And proceeding, we simplify before we multiply. So an 18th. Continuing with this idea of dependent probability where the probability or an event first affects another event, we could do this with a table as well. So this is domestic migration from 95 to 2000 in the U.S. And this is in thousands of immigrants and emigrants. Notice the first thing I want to do is get these sums and then make sure that they equal the same number vertically as well as horizontally to know that I didn't make any mistakes when inputting into the calculator. I am using this information for 3 problems. I don't want to use an incorrect number 3 times and lose credit on all of them. For these problems, you really have to be careful with the wording. For the first example, we want to find the probability that an immigrant is from the West. So Western immigrant. So still usual probability favorable over possible. Our target or favorable is a Western immigrant. So Western immigrant is right there. That's our numerator. Now we are only pulling from the immigrant category or column. So then we want a denominator of 11,656. As a approximate percentage, that's 22.8%. Make sure to write this as a decimal or a percentage because this number reduces, as you can see, both are even. Or you could write the fraction in reduced form. It's just easier now to go with the percentage or the decimal. In the next example, the probability that someone selected from the South region is an immigrant. So it's a different wording, but it's again implying dependent probability. So an immigrant given that they're from the South. So the target is a Southern immigrant. So Southern immigrant, so immigrant is first column and Southern is the third row. So we want a numerator of 5,042. Now we're picking from the Southern region. So this time, instead of adding a column, we add the row for the South region. 8,285. As an approximate percentage, we have 60.9%. So wording is really important here, especially on the next problem. The probability that someone selected is an immigrant and is from the Midwest. Notice this time it does not give us a sub-pool of people to choose from. The first problem said, okay, they're an immigrant. Cool, so that's the denominator. The next problem said they're from the South. Okay, that's the denominator. This time, however, it doesn't specify. So then we are going to use the whole table's values. So the probability that we get an immigrant and that we have a Midwesterner given that we already have an immigrant. So this will be the intersection of immigrant and Midwest, the 2951. That's all over the entire total amount in the chart. As a percentage, rounded, we have 12.7%. You could use the formula for dependent probability and have this equal to the probability of selecting just an immigrant and multiplying that by the probability then of having someone from the Midwest given already that you have an immigrant, and you'll get the same answer, but I think that is a harder approach. Now we will talk about a standard deck of 52 cards to show what dependent probability means. So 2 cards are drawn from a deck of 52. First, we want to talk about dependent or independent and then find the probability. We select 2 hearts the first card is put back or replaced. So for that reason, this will be independent probability. So we'll just multiply the two probabilities together. So the probability of drawing a heart and another heart is equal to their separate probabilities multiplied together. One-fourth of a deck of 52 cards are hearts, so there are 13 hearts in a deck of 52. So 13 favorable over 52 possible. That is for both of the probabilities, or 1/4 times 1/4, which is 1/16 of a chance of this happening. If you take out a card, you have a 1/4 chance of it being red, specifically a heart. Put the card back, draw again, you have a 1/4 chance of getting a heart, but then the probability of getting two hearts after replacing the first card, 1/16 of a chance. Now when we select two hearts and the first card is not replaced, now that's dependent probability because there's one less card in the deck. So we have, when you do the second draw, so the probability of drawing a heart and drawing a heart when the first card is not replaced. So these are dependent, so the probability of the heart draw times the probability of getting a heart after we've already pulled a heart and not replaced. So the probability of drawing a heart, like before, is 13 on 52. But we are assuming that we were successful in picking a heart on the first pull. So then there is one less heart, or 12 left, and there's one less overall card in the deck. So now there are only 51. Simplify before you multiply. We get 1/17 of a chance of this occurring. In the last problem, a queen is drawn, is not replaced, so I'm thinking dependent probability, and then a king is drawn. Yeah, this is dependent again because we're not replacing the card. That affects the probability for the second pull. So the probability of drawing a queen and then a king without replacing the first card is equal to the probability of the queen draw times the probability of picking a king, given that a queen has already been chosen and selected and not put back. Probability of a queen. There are 4 queens in a deck because there's 1 per suit and there are 4 suits. So 4 over 52. And queens, by the way, are known as face cards. All the face cards are Jack, Queen, King. So there are 3 face cards per suit for 12 in a deck. Aces and 10s are not face cards. Now we have 1 less card in the deck when we try the second pull for a king, but we still have all 4 kings in the deck because we pulled a queen for the first time. So the numerator stays the same, but the denominator is 1 less. Multiplying that as a fraction in reduced form is 4 over 663.